right, class. Uh, Welcome to another session on this introduction to heterocyclic chemistry. Now, I'd started talking about orbitals, I think, in Intro 1 or Intro 2, but now I think I just want to bring in uh, uh, something which should have been, I can say it must have been, should have been emphasized earlier, but I felt that I need to bring it up now. And this is the interaction of the orbitals. Now, now we just say, for example, uh, um, you've got something like an atom like hydrogen and another hydrogen coming in to form a hydrogen molecule. Now, in terms of the orbitals, you are saying you've got an s orbital representing one hydrogen and then an s orbital coming together. So I think I would rather put it in this form, that there is one s shell and it is overlapping with another one. I think I would rather put it like two circles like that. In this case, you are saying that you have an s orbital and an s orbital interacting. Okay. Now, uh, in this case, want to look at an interaction between an S and a P. Now, in this case, the ones which you are talking about currently, before we go down to these pi bonds, we are talking about head-on overlap. And the head-on overlap between the orbital is something which you call formation of sigma bonds. Uh, yeah. So uh, uh, those ones are formed by head-on overlap. So in this case, you've got an S and a P. In this case, they are overlapping. So this is the sphere for the S orbital and this is the P orbital. Now, this point here represents the atom containing the P orbital, so that if you've got other bonds like maybe like if it is a carbon, then you're going to put three bonds. Yeah, I'm just trying to give an example of that. Yeah. So what it means is this: if you're talking about a p orbital, in the one which is interacting, there is always a backside of the p orbital which is not interacting on the other side. Please remember that, yeah. Just in this case, like you've got a proton plus something like a carbanion coming together in a sigma bond. This is just illustrating there is a hydrogen here, and then there's the orbital of the p orbital. Please note that there is this other side where there is the orbital which is not interacting. So this one at the center is the carbon atom, and then there are three bonds attached to it. It's just an illustration to that. Okay. Now, this one is still talking about head-on overlap, in this case between a p orbital and a p orbital. This one we are talking about interaction. Previously, we are talking about an interaction between an S and a P and S and a S. So here we are talking about head-on overlap between a P and a P. Yeah. So that in this case, uh, so the overlap will just show. This one is showing the overlap between this orbital and this orbital at this point here. These two are overlapping together. Kindly know that in this orbital, I'm not shading. For example, if you're talking about an orbital, you should either be shading one side and the other is not shading, or you're showing plus and minus. Yeah, that's how they are. But for simplicity case, I'm just leaving them the way they are, unshaded. And later, if we'll be talking about molecular orbital theory, this is just a simplified illustration of the orbitals. But in real sense, when we'll be talking about proper interaction of molecular orbitals, there's something called the conservation of orbitals. So that if you are going to have two atomic orbitals, if they're going to come together, you're going to form two molecular orbitals. And some are going to be bonding, some are going to be anti-bonding. So in this case, what I'm showing are the bonding orbitals. I'm not showing the anti-bonding orbitals. Yeah, keep note of that. So um, uh, uh, at a higher level, at master's level, then you're going to be showing all the possible orbitals, including the non-bonding orbitals. But for now, we're just going to show the bonding orbitals only. Yeah. So this is just a simplified form. There are other orbitals which are not being shown. Now, in this case, I'm just showing an example of an interaction between a p orbital, like now, oxygen bonds with a p orbital. Yeah, the bonding, like the lone pairs, they're in the p orbital, and here you're talking about a carbon. So that in this case, this is an example of a carbon. Let's say there is a hydrogen, and a hydrogen, and then it has something like a chloride, which is like a living group. And now I'm talking about a nucleophile, which in this case is like an oxygen. It is attacking here. So you're talking about a what? An SN2 type of reaction. SN2 type of reaction. Now, you can just try to show an arrow like this one, but it's best to show using the orbitals. Then you'll be able to understand why SN2 proceeds via backside displacement. And this is what happens. That if for example for example, if you have to say the nucleophile comes from the comes from the yeah, from the frontier, it will mean that its orbital is going to come to from this side, and it's going to interfere in the bonding between the carbon and the halogen to which it's going to be attached. But if it will be coming from the back, then it will find the side of the orbital which is not bonding to the uh, the living group, and it must come from the back in an so that uh, if you are to draw a line, there will be a 180 degrees between the incoming nucleophile and the living group. And this is something which I think you learned maybe in earlier, earlier classes, but I think you did not understand. So the nucleophile has to come from the backside, and then the living group is living at the frontier. So here, this one is coming, and then at the end of it, uh, so this is what you had like the OH here. I'm just showing the hydrogen, the oxygen bonding with the hydrogen, the sphere of the hydrogen, and then this part does not change, and then this part of the orbital is overlapping with the carbon, and then the carbon, the halogen which was attached to it has now left. I would have put this X over here, but I've just put it down. Yeah, I hope you'll be able to see it in its context. Yeah, all right. Now, the orbitals which are of importance, of great importance to heterocyclic chemistry, are the pi bonds. Pi bonds, pi bonds, pi bonds. So in this case, the pi bonds are formed by sideway overlap of the p orbitals. The ones which you've been dealing with, this was head-on overlap. But then sideway overlap is just a small overlap. So that means that a pi bond is easier to break than a sigma bond, which is formed by head-on overlap. Now, in this case, I've shown example of something which has been shown in textbook. Maybe I've got a carbonyl group, and then I've got a group like a nitrogen, which is attached to a double bond. In this case, this double bond is a carbonyl. And you say, hey, you've got an atom next to it donating electrons, and then the electrons are going to end up to the oxygen. So you're going to end up with this atom attached to it, having a positive charge, and then the oxygen having a negative charge, something like that. But in illustrating with an orbital, then things are going to become very easily, because you are just saying that um, just to give an example, let me just try to see whether I can illustrate here. Excuse me. And you're just going to see how this thing is going to make a lot of sense. Yeah? Okay. Oh dear. No. Okay. Should I'm not seeing another atom. Okay. I'm not seeing many of those colors, or should I? Okay. Uh, okay. Let me see how I can put it. Uh, for this one, I think rather than posting, I think I don't appear to have many of these ones which have got these ones of the orbitals of many colors. But let's assume the one at the center is your carbon, yeah, and this carbon is overlapping with your what? Okay, let me say, let me remove that one. What I have here is what I'm showing as my carbonyl. This is my carbon, this is my oxygen. Okay, so this is a methyl group, yeah? It's attached to the carbon group, yeah? Can you see that? So here, this is your pi system. So the electron, so there's the pi system, there's the electron cloud at the top and the bottom, yeah? So this is your double bond, and and the oxygen withdraws electrons. So this pi bond is electron deficient, but I can make it electron rich by attaching an electron donating group. So now in this case, if I'm going to attach another group here, can you see what I'm doing here? Okay, if I'm going to show it like this one, yeah, I'm now ending up the atom which I've attached, which like in this case is my nitrogen. This one here, it contains the lone pair. The lone pair is in an orbital which is overlapping with carbon, and this carbon is overlapping with the oxygen. So you have three p orbitals which are parallel to one another. So the electron density can pass from this the lone pair on the oxygen to the carbon and then to the oxygen. Can you see that? It is flowing from this one, from this nitrogen containing the lone pair to the carbon, this part of the double bond, and then to the oxygen. So this is what is being shown here. That I've got my nitrogen here, it's overlapping with carbon containing the oxygen here. So what you're saying is that in this environment, the lone pair on the nitrogen can overlap like this one, and then it donates electrons to the carbonyl. Eventually, you're going to end up with the electrons on the oxygen here. So so this one can be a bit tricky to show here, but if I'm just going to show here with the orbitals, in this case, we're saying uh, this lone pair is donated to this carbonyl group, and the end of it, this nitrogen which is donated becomes positively charged, and then the electrons flow to the end, to which the oxygen at the end attains a negative charge. Can you see how the electrons are flowing in a straight line, provided the orbitals are parallel? So if I put it at an angle, it is not overlapping. So for the atoms to overlap, they need to be parallel, and if possible, they need to be of the same size. So that means that if the atom which is donating electrons has got a very big orbital, like a like a what? Uh, like the what? Like rather than nitrogen, I'm talking about something like a halogen, like maybe bromine, which has got a 4p, and or even iodine 5p and 6p or orbitals and the rest. Yeah. So in that case, the overlap between the 6p and the 2p will not be very good. So you need to have a 2p and a 2p example, for example, that will allow good overlap between the p orbitals. Yeah. The important thing is that the the orbitals have to be aligned parallel. Okay, all right. Okay, good. So let's go to more about the carbonyl group. Yeah. Oh dear, let me